So what is dark matter? It's pretty unusual stuff, but it is amazing how much we have learned about the stuff that we have had experimental results on so far, and stuff that makes up us and stars and things like that. And we've learned a lot from measurements in physics, astronomy, and also in how it all fits together in the theory of cosmology, which is how the universe has evolved. So dark matter is one of the elements of this theory. And I'll show you in a moment how we understand that it is a necessary part of our total composition of the universe, although we've only really learned about it through its gravitational effects so far. What we'll talk about today is how we may learn more about it by determining how it interacts with ordinary matter like us. So let's start by reviewing the physics of fundamental particles to show what we know and why we think that dark matter may be something completely different. So the current theory of elementary particles, usually referred to as a standard model, classifies basic particles that make up our universe as quarks or leptons. Quarks are in 3 generations, as are the leptons. The ones that we're familiar with are the ones that make up our protons and neutrons that sit inside the nucleus of our atoms. Those are the up and down quarks, as they're referred to. Charmed, strange top and bottom quarks are heavier versions of the same thing that have been observed in high energy experiments with accelerators and in cosmic rays. The 2 up and down quarks form the protons and neutrons, and then an atom is formed by those protons and neutrons being in a nucleus at the center of the atom with electrons, which you see down at the bottom here, going around the nucleus and forming the chemical elements that you're familiar with. There are other particles referred to as neutrinos that have counterparts with the electron and its heavier partners, the muon and tau particles. Used in some forms of radioactivity, but naturally emit neutrinos, believe it or not, in very, very small quantities. And they're also produced in the core of the sun by the nuclear reactions that power it. And in fact, the SNO project was observing those neutrinos and from the measurements, inferring that they have a small mass, along with experiments done in Japan that did the same thing for neutrinos produced in the atmosphere. But just to give you a feel for how little neutrinos interact with things, there are billions coming from the sun at the present moment. With a detector the size of a 10-story building, we observed 1 neutrino an hour with the Sudbury Neutrino Observatory original experiment. The blue on the particles on the right are what we refer to as the force carriers. Photon for the electromagnetic force, the gluon for the strong force, the Z and W particles for the weak force. And in addition to that, we have the graviton for gravity, which is not shown in this figure. The Higgs boson gives mass to all of the particles except neutrinos that appear to obtain their mass with a different mechanism. And for each of these particles, there is an antimatter particle that has been observed. And we think that in the early universe, energy was converted into mass and antimass in equal quantities. And so particles and antiparticles would have been created out of the energy that came forth in the original Big Bang. Dark matter particles, based on what we've seen so far, do not share any of the properties in common with any one of these particles, and therefore we think it must be a new form of matter. that's why we want to observe it and understand its properties, and that's what today is all about. Now, we have quite a robust theory of how the universe has evolved since the original Big Bang about 14 billion years ago. And this has come about from many measurements in physics and astronomy, along with the theory of cosmology. And let me tell you a bit about that, and then the others will tell you about the experiments we're doing today to try to understand more about dark matter. So here's the overall story of today of what we think the universe evolution looks like. On the order of 14 billion years ago, there apparently was an enormous explosion. We only really know what we can learn from the information following that explosion. We don't know what happened before it. We don't know what caused it, because it's very difficult to observe anything. And scientists base their judgments on things that they are able to observe and measure. The theory suggests that that explosion liberated a tremendous amount of energy. And in about first 10 to the minus 43 seconds, there was a tremendous expansion referred to as inflation, where the whole universe went from the size of an atom to the size of a grapefruit. And then it continued to expand after that. At the point where about 10 to the minus 32 seconds, when you're still dealing with 10 to the 27 degrees centigrade as the total temperature, everything has been created from energy in the form of matter, equal amounts of protons, of particles and antiparticles, quarks, neutrinos, and electrons and their partners. And as the universe cools off, then the quarks begin to coalesce into neutrons and protons at about 10 to the minus 6 seconds. After about 3 minutes, we're at the point where those protons and neutrons can form nuclei. After about 300,000 years, you actually have the electrons joining on to form neutral atoms. And finally, at that point, light can shine through. And that has been a very big element of our ability to understand what has happened that leads to this narrative I'm describing to you. The so-called cosmic background radiation is the light that has come through after about 300,000 years of evolution. It's about 2.7 degrees above absolute zero now in terms of the way it has cooled off. And it's one of the things I'll talk to you about in terms of the information that we obtain, which leads us to this theory. Another big question is the influence of dark matter. And I'll show you that we understand that dark matter makes up about 5 times the mass of everything glowing that you see when you look out on a starry night. There's about 5 times as much mass between the stars as in the stars and galaxies themselves. That influences significantly the formation of galaxies, stars, and the coalescence of those galaxies into the universe as we see it today, about 14 billion years after the original Big Bang. Now, how do we know that? Well, one of the things that we're able to observe is this 2.7 degree radiation. And that's been done with exquisite measurements, originally on Earth and most recently in extremely good satellite measurements. The picture on the left shows you the variation in the amount of this radiation. The variation is only about a part in 100,000. But that variation can be expressed, in this case, its variation across the sky can be expressed in the way shown in the figure at the bottom. These are actually polynomials of order L as plotted along the horizontal plot, and the amplitude in the vertical direction. If you look closely, you can see little dots, which are the data. And the average of the data is, in fact, the red points. But the blue line that goes through them is a theory of how the universe has evolved, involving ordinary matter and dark matter that has cooled off itself to a very low temperature. And the fit you can see is extraordinary. And there are really only 6 parameters in the fit. It's an amazing accomplishment. But it suggests very clearly that there is about 5 times as much dark matter in mass as there is ordinary matter. And that's borne out by looking at galaxies like ours, like the Milky Way, which is a spiral galaxy. You see another one, it's actually, I think, a cluster of galaxies, but it's in a form that kind of looks like a cinnamon roll. And the reason we see a patch across the sky called the Milky Way is that we're looking at the edge of it. So we're looking through it. But if you plot the velocity of matter as a function of radius, you see this plot in the upper right. And what you find is that you can't explain it with the amount of matter that is there that is glowing. That would be the line labeled as disk. What you need is about 5 times as much mass in a form that's referred to as the halo, which is thought to be dark matter. It's not glowing, you don't see it, but it influences it through gravity. We come to a similar conclusion in this factor of 5 more mass in dark matter by looking at the universe as a whole, which can be done remarkably by lensing light from behind, from a bright source behind other matter, producing, due to the laws of general relativity, images that are shown as the bright blurry images on the left in this telescope picture. A similar conclusion is drawn that there's about 5 times as much mass in dark matter. And finally, in terms of the fact that it is quite weakly interacting, it's quite a beautiful example of this. There are many ways in which that's concluded, but here you see two clusters of galaxies that have collided, and they've already passed through each other. But what you can see is that the ordinary matter, which is imaged in X-rays, is the pink material, the pink section in the center. If you do this gravitational lensing process to see the total mass, or the remainder of the mass other than the X-ray imaged material, you see the two blobs that are in blue in this picture. It's quite clear that the dark matter has moved through much more quickly, much less impeded by collisions, which is what happened to the pink ordinary matter. And so our conclusion is that dark matter interacts very weakly. So overall, putting all this evidence together, one concludes that at least one way to describe dark matter is in the form of particles that are weakly interacting and are massive. Massive comes from their influence on how material forms in the formation of galaxies and so on. So weakly interacting massive particles, or WIMPs. And scientists have a certain sense of whimsy, and WIMPs is a fun term to use. So that's a major topic for today. And we're a bunch of geeks looking for WIMPs, you might say, if you really want to characterize today's discussion. Sorry for that description of my colleagues. I'll just accept that for myself. Major topic for today. There is another candidate, which is particles referred to as axions. They have very different properties, and we're not going to try to address them in our discussions today. So our final picture of how the universe is made up has 3 major components: matter, us and the stars; dark matter, which we've just discussed, and a final one referred to as dark energy. And it's quite remarkable how the 3 of them fit together, and they also fit in those models of cosmic microwave background. Dark energy has been inferred by studying supernova at the farthest distances in the universe. And they found, when measuring them, that they are accelerating more than is expected. They're able to measure how fast they're going through the redshift and how far away they are, because they're a very standard supernova. They always give out a certain amount of light, and they can just tell by seeing how faint they are. This requires that there's a repulsive force added to the attractive force of gravity. And so what you've learned in school for years, that gravity is always an attractive force, is violated to a certain degree, not here on Earth in a noticeable way, but in terms of its influence on how the universe has evolved. And that's also the subject of very different experiments from what we're doing for dark matter. So we're after dark matter. And how do we go at it in terms of trying to get new properties determined? Well, we're in a universe composed of matter. We want to use that matter to try to observe more properties of dark matter. And so we have to have essentially an interaction between the dark matter and our experiments made of ordinary matter. And so there are predictions of what that dark matter might be, ways of expanding the standard model in acceptable ways to include dark matter. Too many theories for us to discuss them in detail at all today. But the make it, break it, and shake it you're about to hear about are basically ways of how dark matter interacts with ordinary matter. Perhaps by creating enough energy in ordinary matter, you can make it. Perhaps by observing it to decay, or perhaps interacting with itself, referred to as annihilation. You may see ordinary particles that you can detect, and that'll be discussed under Break It. Finally, it's more complex than this, but essentially what one is looking at is having the dark matter hit atoms and having them recoil like a billiard ball. And that's the shake it part of our discussion.